Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to go over acid strength and the acid ionization constant, also known as your Ka. So let's get into this. So first we need to talk about strong acids and weak acids. So strong acids are acids that are going to ionize completely in solution. So there are three, so these are going to be your six strong acids. So you have HCl, HBr, Hi, HNO3, HClO4, and you have H2SO4. So H2SO4, sulfuric acid, is a diprotic acid. The rest are monoprotic acid. Monoprotic because they all have only one acidic hydrogen that will come off when you put it into water. Here you have two hydrogens that will come off when you put it into water, so it's diprotic. Okay, so those are the six strong acids, and what that means is, again, they completely ionize in solution. So when you throw them in water, they are going to completely ionize into their ions and separate. So much so that you'll have none of this left over and all of this will be what's left. So HCl is a good example. So here we have a strong acid. When you put this in water, what happens is that the hydrogen and the chlorine ionize completely, such that you don't have any more of this. So all of this is going to ionize and separate into their ions when you have H3O plus, which is your hydronium ion, and what's left is the chloride ion. So this is what's left in solution. So you'll see here that we have a single arrow going this way, and what that means is that there is complete ionization. So none of this is left when you get this, when you have this sort of reaction. So basically what happens is if I start with 1 mole of HCl, let's say I start with a solution and I have 1 molar HCl. So that 1 molar at the end of the reaction, when it reacts with water, is going to be 0. So this is going to go to 0. I have none of that left over, and all of this becomes hydronium ion and chloride ion. So I'm going to end up with 1 molar of your hydronium ion, and the concentration would be 1 molar of your chloride ion. So all of this became these two. So that's what it means by to be a strong acid. So here, what about a weak acid? Well, a weak acid means that it hardly dissociates or ionizes at all. So there's a partial ionization such that there's a tiny bit will ionize, but most of it will stay in this form. So HF is a good example. You'll notice that HF is not one of the six strong acids. So any acid that is not one of these sixes is six acids is a weak acid. And if it's a weak acid, excuse me, sorry. If it's a weak acid, that means that it will only ionize a little bit. So it partially ionizes, but not completely. So most of what you have in solution is going to be in this form. So the H and the F stay together, right? So hydrogen and fluorine are going to stay together, and it's going to stay in this form, okay? So you'll get a little bit of this will ionize to form a little bit of your H3O plus, your hydronium ion, and a little bit of your fluoride ion. So there's going to be a little tiny bit of this in solution, but most of it is going to be in this form. So that's what we mean by a weak acid. So this goes back to what we learned about weak and strong electrolytes, right? So remember, electrolytes are things that they form ions in solution. So for example, your sodium chloride salt. So if you put an electrolyte in water, it's going to be a strong electrolyte if it completely dissociates in water. So if your ions completely dissociate in water such that the only thing that is in solution are the ions and not the compound, then that is a strong electrolyte. If it's a weak electrolyte, that means that most of it stays together, but a little bit will dissociate into ions. So that would be a weak electrolyte. So we use the same definitions to refer to weak and strong acids. Okay, so and then we use this double arrow. This is the equilibrium arrow to suggest that this is the equilibrium, and this indicates that you have partial ionization. Okay, so another way we can talk about this is how far we're talking about the equilibrium. When we're talking about strong acids mean that they dissociate completely. So their equilibrium is going to lie far to the right. So that's what we mean by a strong acid. If their equilibrium lies far to the right, such that it favors the products so much and not the reactants, that means that it's going to be a strong acid. So strong acids have their equilibrium lies far to the right, favoring the products. If it's a weak acid, then that means that the equilibrium lies far to the left. So the equilibrium is going to favor the reactant side very much, so that most of what you have in solution is going to be reactants and not products. So you're going to have a lot of this, your HF, together in solution, and just a little tiny bit of these two in solution. So weak acids have their equilibrium lying far to the left. Strong acids have their equilibrium lying far to the right. So that's another way to understand that. And so one of the things we need to keep in mind is why are some things strong acids, some things are weak acids? What's the cause of that? And that has to do with the attractive force between the anion and the H plus ion. So the stronger the attractive force between the anion and the H plus, then that means it's going to hold together more strongly compared to the attractive force of the ions to water. So if the attractive force between H and chlorine is very, very weak, then the attractive force to these two ions or these two elements to water is going to be, if that's stronger than the attractive force between these two, then the water is going to pull them apart, and you're going to get most of this, if not all of this, in water. So the weaker the force between the hydrogen and the anion, the stronger the acid, the more likely it's going to be pulled apart by water, and the attractive forces of the water to these two is going to be stronger, and therefore they're going to be separated more easily. So the attractive force between these is what determines the weakness or strength of the acid. So for this strong acid, the attractive force of the chloride ion to the H plus ion over here, this is so weak compared to the attractive force of water to these two that they come apart pretty easily, that they ionize pretty easily in water. Now, if you compare that to HF, the attractive force of the fluorine to the hydrogen is so strong compared to the attractive force of the water to these two, is that so that these two are not going to come apart very easily in water. So they're going to stay together because the attractive force is stronger. So here the attractive force between H and F is so strong, is stronger, so that they don't come apart very easily. So only a little bit is going to ionize in water. So here we see that the stronger the attractive force between the anion and the hydrogen, the weaker the acid. So the weaker the acid. So weak acids have a stronger attractive force between the anion and the H plus, or the hydrogen, compared to that of the strong acids. The strong acids have a weak attractive force between those, and so they're easily pulled apart by the water, and so that's what makes them a strong acid. So the stronger the attractive force between them, the weaker the acid. And so because of this, we know that the stronger the acid, the weaker the conjugate base, right? So the stronger the acid, what does that mean? If the stronger the acid, that means that the weaker the attractive force between the anion and the H. So stronger acids have a weaker attractive force, and therefore they're going to have a weaker conjugate base. So you can see that here. So if this is a strong acid, that's going to separate and ionize really easily, such that the arrow goes pretty much completely in this direction. The reaction goes in this direction completely, so that the chloride ion, which is your conjugate base in this reaction, is so weak that it's not going to go back this way. The conjugate base, the chloride ion, is not going to take back the hydrogen. So this is going to be very weak. So this strong acid, this is a strong acid, and this is a weak conjugate base. Okay, so same thing here. So here we have a weak acid. So these are going to stay together because the attractive force is so strong. And then that's going to produce a strong conjugate base. So this fluoride ion is going to readily take hydrogen back from the hydronium to go back this way. So this is going to be a relatively stronger conjugate base compared to this conjugate base here. So this weak acid produces a relatively strong conjugate base, whereas this strong acid produces a relatively weak conjugate base. Okay, so finally, the last thing I want to talk about is what is known as the acid ionization constant. How can we measure the strength of an acid? Well, this is how we do it. So here I have a generic equation for an acid. We normally represent an acid as HA, A being the anion, H being the hydrogen, the acidic hydrogen that comes off. So HA in aqueous plus water. The hydrogen will donate, the hydrogen will be donated to the water to form hydronium ion, and then what you have left is the anion. And so this is a generic equation for an acid in water. We can simplify it by getting rid of the water and just instead of using hydronium for the H plus ion, we can just put the H plus there. So this is a shortened version of this. So you have HA breaks apart or ionizes into H plus and A minus. And so the ionization, the acid ionization constant, is exactly the same as what we would call the equilibrium constant, but the equilibrium constant in this case is pertaining to the reaction of an acid in water, right? So same setup. So here we have our products. So the equilibrium constant, so this is an equilibrium for a weak acid. So for the weak acid, it's an equilibrium, and so we need an equilibrium constant for the acid. We call that the acid ionization constant. And so we set it up exactly the same. We call it Ka, the acid ionization constant. That's going to be equal to the concentration of the products raised to their coefficients. The coefficients are powers, so these are 1 and 1, so the powers are 1 and 1. and then divided by the concentration of the reactant, which is HA, and that's on the bottom. So it's set up exactly like your equilibrium constant. And so it'd be the hydronium concentration of hydronium ion multiplied by the concentration of your anion divided by the concentration of the acid. Or another simplified way to put it is the concentration of H plus multiplied by the concentration of the anion divided by the concentration of the acid. And so this is what we would use to identify or determine the strength of an acid. So the larger your Ka value, the stronger the acid. So remember, so if you have a strong acid, remember, strong acids are going to ionize completely all the way over here. So the only thing is left is the concentration of H3O plus and Ai, or H plus and negative anion. You're going to have 0 of this, or very, very tiny. So that means if you plug H plus and A minus in, these are going to be very large, and this is going to be very small. So your Ka value should be very large. So if you get a large Ka value, that indicates that you have a strong acid. However, if it's a weak acid, that means you're going to have a lot more HA in solution and a tiny bit of H plus and A minus. So if this then is going to be small in the numerator, and this is going to be large in the denominator. So that means that your Ka value is going to be very small. So for a weak acid, you should have a small Ka value. So small Ka values are going to indicate weak acids. So I hope this is helpful. If you enjoyed this video, if you learned something from this video, please hit that like button, subscribe to my channel, make sure that you hit the notification bell so you can be notified by other videos, other great videos I put out. If you have a comment or a question, put it down into the comment section down below. And thanks for joining me. Have a great day.